Of the course, we gave many examples of differential equations and ordinary linear ordinary differential equations as well as linear partial differential equations, and we learned how to solve them using the method of Laplace transform. So I'm not sure what else to say about that, except that you can refer to my last week's videos where I have done solutions of differential equations using Laplace transform techniques. So any other questions, if you have them, you can write on the chat box and I will. So one thing I would like to say about this course is even though it was accessible to students even outside mathematics, I took a mathematician point of view, being a mathematician myself. So it was not the usual Laplace transform course that you would find anywhere else. There are plenty of resources now on the internet where people take a direct approach, but I took a more, let's say, a more fundamental approach to the problem because I discussed what is an improper Riemann integral, because that's how we define Laplace transform. And I discussed their convergence properties when they exist and when they don't exist. I give examples of improper Riemann integrals that don't exist. And so it is important to learn about this so that when you are ready to apply Laplace transform technique uh, for solving your problems, then you would really need to know what you are doing. Otherwise, you might end up with the wrong answer. So what I found was that there are many gaps in the literature where people are not careful about convergence properties on interchange of limits and integrations and so on. And even though they arrive sometimes at the right answer, but the method is wrong. So um, as a mathematician, it bothers me to see that this kind of techniques are used which are not correct. So I decided to uh, at least, because it's a short course, so I decided at least that students should know where the possible pitfalls are, where one could go wrong with the calculations. And for example, many people don't know when a limit and an integral can be interchanged, that it is not possible always. And so these are subtle mathematical questions that arise in calculus, integral calculus. And one should know that things can go wrong quite quickly if you're not careful enough. So one has to be really careful when you're doing a computation, and when you're reading from a book. It's also important to double check whether their methods are correct or not. And like I said, I found many mistakes in the literature. And so even if you arrive at the right answer, you have to check all the intermediate steps, all the assumptions that you have for all these properties. For example, for the properties of the Laplace transform, initial value theorem, the final value theorem, one has to check that the assumptions under which these theorems are valid are actually being fulfilled by your particular example at hand, so that you are ready to apply it and that you will get a right answer. So it's quite easy to apply wrongly these theorems and arrive at incorrect. So the idea in this very short course, it was only 4 weeks, was to just give a hint where things can go wrong mathematically, and to be careful enough so that when you are actually solving a problem using Laplace transform, you can always go back and check that all the assumptions that were there that you want to use for applying a theorem or so on, a property, those are fulfilled. So that's my take on the subject anyway, and hope you have enjoyed this course, even though it was quite short and we had barely enough time to cover the topic. So, of course, I received many uh, comments in the feedback that I should have given more examples. Trust me, I would have loved to give more examples, but time is was already short, and even though it was a 10 hours course, I think I went uh, quite a bit beyond that. It was in the end about 11 hours. And even then, I couldn't cover everything. So time is short, so one has to pick and choose what you want to present. And so, but of course, if you want to learn more, you can still ask me questions on the discussion forum, and I will answer your questions. So I saw that still no questions on the chat box yet. So I'm still waiting for your questions. There was only one question from the group forms that we sent out from NPTEL, and that was about examples of differential equations, which we already saw in the lecture. Repeat those things. You can just refer to my lectures in the last week's lectures, and there I've given a detailed overview of how to solve ordinary differential equations as well as linear partial differential equations. What we also couldn't cover in this course was the inverse Laplace transform. I mean, we defined it only so we can in this course we only were able to the inverse Laplace transforms if we know what is already there. There is a method to find, given a function in the s variable, there is a method to find the inverse Laplace transform. This is through complex contour integration, and of course it was a too short a course to cover these subjects because one has to go into complex variable theory, and also that many of you might not have covered those topics yet in your studies, so I did not take it up. So the only things that were required for this course was the basic integral calculus and differential calculus. So many of the theorems of integral and differential calculus, I hope you were able to revise and learn better because it was being applied here in this course. And those are some fundamental things that even if you're not a mathematician, even if you're not studying mathematics as a subject, um, even if you are an engineer or someone else, you still won't need those concepts in order to apply. For example, if you want to model a real world problem in terms of differential equations and you want to solve them, then of course you need techniques and you need to learn them well so that you can apply them well in your to solve your problems. So even though it was basic integral and differential calculus, I think some of you might have difficulty in the beginning because uh, there were might have been some gaps, and I did not recap all these topics like Riemann integration and so on, which are important to know, and I took them as granted. But I hope you were able to revise them during the course, and so that you are able to understand what is an improper Riemann integral, because an improper Riemann integral is defined using an ordinary or a proper Riemann integral. Okay, so enough about the course. Now I'm still waiting for a question. Please feel free to ask any question that you want, and don't worry whether what other people would think about it. So be bold and ask as many questions as you want. Let me just check once if there are any other questions from the Google Forms. No, no questions yet. No more questions? Okay, I'll wait another 3 or 4 minutes. If not, then we can close this session because there are no questions yet. So many of you complained about difficulty of assignment problems. So they might have seemed difficult in the beginning, but once you get to learn the subject, you will see that they were not that difficult. They were probably tricky, but not difficult. I mean, in the sense that they were almost always the questions were designed so that you can apply, knowing the assumptions well, you can apply a theorem or a property, and you can quickly find the required formulas. I hope. Okay, so there is a question: why Laplace when Fourier series is there? Okay, good question. Um, so the Fourier series is not admissible for a large class of functions. So if you have learned about Fourier series, it is well defined on a class of functions which are square integrable. In terms of mathematical function analysis, it's they are in L2 functions. But as we have seen, the Laplace transforms are actually admissible for a much larger class of functions, which are um, of exponential order. So an exponential order function is of course can if it grows too fast, it may not be square integral. So the Fourier transform might not exist for such a function, but the Laplace transform will exist. So that's the reason Laplace transform is chosen. It's not a good question. Any other questions? So there are also other kinds of transforms, and what so if you remember, I talked about integral kernels and integral transforms. So there are many other kinds of integral transforms, and the integral kernel that has to be chosen depends on what kind of problems you are dealing with. So different kinds of situations is for different kinds of integral kernels to be applied. And the Laplace transforms is especially well suited to differential equations. Uh, and even you can solve, you can solve uh, recurrence equations, integral equations, and so on. And so really, it depends on what kind of problems. But the main issue is that the Fourier transform may not be applicable in many situations, but you can still apply Laplace transform technique. Okay, another question is about the use of Laplace transforms other than solving differential equations. Okay, so we have seen in the course that um, apart from solving linear ordinary differential equations and linear partial differential equations, it can be solved. It can be used to solve, for example, integral equations. It can be used to evaluate integrals. It can be used to solve integral differential equations, so which have both an integral term and a differential term. It can be used to solve what are called recurrence relations, and then or reference or difference equations. They are also called sometimes. So yeah, and even a mixture of differential equation or difference integral or so depending on the applicability of the Laplace transform. So of course the Laplace transform is not applicable always, and I gave even for very simple ordinary differential equations, the Laplace transform technique may not work. So one has to assume some properties of the solution in order to apply the Laplace transform. So, of course, you have seen the Laplace transform works well when you have a piecewise continuous function, which is of exponential order, or if it is not piecewise continuous, say at near zero, then it should satisfy some other condition for the Laplace transform. So, under very specific conditions, the Laplace transform exists, and we have to assume that the solution should satisfy these types of well-behaved has to satisfy these good behavioral properties so that Laplace transform techniques can be applied. Yeah, so other than solving differential equations, we have covered in the lectures. We can solve integral equations, difference equations, recurrence relations, and even a mixture of all these types of equations. Okay, another question. Can you tell us how we can find Laplace transforms of the modulus? I don't understand what is modulus. Do you mean the mod function, mod of x? If it is the simply the absolute value function, and since we are only restricted ourselves to, okay, yeah. So since it is a modulus function and we restrict ourselves to functions only on the non-negative real line, so from 0 to infinity. So the modulus function is just the function. So if you take fx equals mod x, then in the positive or non-negative real line, it is simply x. So then the Laplace transform, we have already seen the Laplace transform of this function ft equal t is given by 1 over f squared. So that's just if I have to find modulus of sine of t. Okay. Okay, so when you take the modulus, so this is a very specific example. Okay, so the modulus of sine t is a very specific example because it is a periodic function of period pi by 2. When you take the modulus, it becomes a periodic function. And then you can apply what you know about periodic functions. So you can find the Laplace transforms of modulus of sine. I'm sure you'll find it in many textbooks. It's that. If you don't find it, just put me an email in the discussion forum and I'll write down a detailed solution. Okay? Does that answer your question? So you just have to apply what you know about periodic functions, and you can then find uh, the Laplace transform of modulus of summation. Okay, good. So any other questions you have, you can ask now. So I hope many of you have opted to take the exams. Uh, so if you still have any doubts or any questions you have, you can still post until the exams. You can still ask me on the discussion forum, and I'll be happy to answer your questions there. This time, NPTEL courses are doubly difficult for both for those who are preparing the courses and for those who are following the courses because of the pandemic. Uh, okay, another question. What's your course name on NPTEL? It's just called Laplace Transform. So I'm actually having two courses on Laplace on NPTEL. One is on Laplace transforms, and the other is on measure theory. But the measure theory one is pure mathematics, and it is supposed to be for master theory. And the Laplace transform course is also open for undergraduates as well. So you can simply search for Laplace transforms, but you can not enroll because the enrollment has not. In fact, the course has finished. So, but you can, I think you can still find the video lectures posted on NPTEL. Yeah, you're welcome. So, any other questions you have, you can ask. So, some of the material, in fact, that I decided to present this course, it is difficult to find the details in many of the textbooks that at least they saw. Uh, so these were mostly textbooks meant for engineering background students, and many of the details are missing. So I hope that you, if you pay, if you have followed this course keenly, then you will see that there are many details that one has to be careful about, so that you don't make mistakes in the computations and this can, I think if you have followed the discussions in the discussion, then you would have seen that it is very easy to make such mistakes, and sometimes you might get uh, correct answers just by pure luck, but at other times, it definitely get wrong. Okay, another question. Please give some explanations about exponential functions and its properties. So the exponential function is very special function because uh, probably because it is very well behaved under differentiation and integration. So uh, also because okay, so let me first explain about the exponential function. So in the sense of Laplace transform theory, functions of exponential order are well behaved, meaning that functions that do not grow faster than the exponential function. So let me try to draw a picture. So so here you have the Cartesian plane, and this is the line y equal to x. So this is the y-axis, and this is the x-axis, and this is the line y equals x. Okay. Now the exponential function starts at 1. This is 1, and it grows quite pretty fast, and it has an exponential curve like this. So this is f(x) y equal to fx equals e to the power x. So even if you take e to the power alpha x for some positive constant alpha, then also it will look like this. Okay? On the other hand, if you have a negative constant, then it goes to 0 as x goes to infinity. So this is for alpha positive, and this is for alpha negative. So this is y equal to e to the power alpha x for alpha negative. Now, I'm sure you would have heard exponential growth a lot during these last few months. So exponential growth means that uh, the function moves very, very quickly. And in terms of Laplace transform theory, function will have a well-defined Laplace transform, provided it is piecewise continuous and it has what is called an exponential order. An exponential order function is something like this. So it can have even it can be more than it can go above the of the exponential function from small values of t or something like this. But it will never so after some fixed point, so after this point, it will lie below the curve of the exponential graph. So this is a function gx with exponential order. So if you remember in the first week, we saw in the assignments functions of exponential order, functions of logarithmic order, and functions of polynomial. So there is a hierarchy of functions where first you start with bounded functions. Bounded functions means when you take the limit to infinity, you get a finite value, or it can oscillate even, but um, it cannot go to infinity, plus infinity or minus infinity when x goes to infinity. So once you can start with bounded functions, then you can go to logarithmic order functions, which lie below the curve of the logarithmic function. So the logarithmic functions is something like this. This is the logarithmic function y equal to log x. So if a curve starts somewhere like this and it goes below the logarithmic curve, then it is of logarithmic order. Similarly, you can also have other functions which rise as the power of t to the power n. So these are called functions of polynomial order, and they lie somewhere between functions of exponential order and logarithmic order. So here you can have functions. So if you have t to the power n, then it starts at 0 and it will grow something like this. It can even oscillate a little bit depending on your polynomial. But so this is a typical uh, curve of polynomial order. So this curve, this green curve is a polynomial order. This is of logarithmic order and this is of exponential. So these are various types of growth conditions that one can put on the function so that it is well behaved near at the well near infinity. So when you go to larger and larger values of x, the growth conditions are put in place so that you have a nice behavior of the function at infinity. So for Laplace transform, exponential order growth is very important because once you have exponential order for a piecewise continuous function, then the Laplace must exist. So this is the significance of exponential order functions in the theory of Laplace transforms. And many of the real world situations that you encounter, you will find that there are functions of exponential. So this is why Laplace transform techniques are so useful in the physical sciences as well as the mathematical sciences. So because it can model, it can be used to solve models that are based on real world situations, and the Laplace transform techniques are very, very powerful tool to solve such problems. So I hope that answers your question. Okay. Fourier transform versus Laplace transform. So I think I've already answered this question. So the Fourier transform is applicable for only a smaller class of functions, which are square integrable, but the Laplace transform is applicable for a much larger class of functions. So in that sense, the Laplace transform technique is a little more useful than the Fourier transform. On the other hand, the Fourier transform satisfies many, many more useful properties that makes it more a richer theory, mathematical theory, which can be applied to some real world problems. So there's both a positive and a negative side. So if you can use Laplace transforms but not Fourier transform, then of course you'll go ahead and use Laplace transform. But if you have a choice of both, then many people choose to use Fourier transforms because it has a much richer theory and it is much better behaved uh, in terms of L2 functions. Okay, what do you mean by function of exponential order? So this is exactly what I described now. I mean, you might have missed it. So you can just go back to, so this video will be available for you to watch. You can just go back and watch a graphical, intuitive idea of what an exponential function is. So in terms of just informally speaking, it is a function which does not grow faster than an exponential function. So in terms of graphs of the function in our tool in the Euclidean plane, you will see that after some time, the graph of the function of exponential order must lie below the graph of the function of an exponential function. So this is what it means uh, to be a function of exponential order. Okay, more questions. Second year engineering student, which math book to follow? So I'm not sure whether you mean uh, so the book is about you want to learn Laplace transform or not. But so I gave I think three recommended book in the course outline, you can go and check the course web page, and you will find there three courses, three books that are recommended for the course, and those three books are written. So they are on the one hand, one of the books is especially designed for engineering students. I think you might have heard of it, which is by Ellen Tracy. And this is I think it's called Mathematical Tools for Engineering or something like that. I'm not sure the main title of the book, but Elvin Tracy is a very well-known book. On the other hand, uh, there are two other books. One was on, I think, on Stone City, which has lots of problems. So you can um, use that book to solve many more problems. But you have to be careful because it is lacking many of the details that I provided during the course. So it gives you a balance between practice and theory. So for theory, you can go back to my lecture notes or lecture videos, and for practice, you can use the Schnorr-Series. Now there was another book, or rather another two books, if I'm not wrong. So one was by Schiff. Uh, so this Schiff book is more mathematically inclined because it talks about convergence issues of the improper Riemann integral and so on. So it's the balance between uh, the engineering point of view, which disregards many of the subtler mathematical problems, and but it also tries to give some of the mathematical aspects of the theory. So it's a nice balance between the two. On the other hand, if you really want to study Laplace transforms at the level of only pure mathematics, there is a very nice book uh, by Gustav Deutsch. I'll just write it down. So this is a book by Gustav Deutsch, and I think it's called Introduction to Laplace Transforms. But I must warn you that this is a pure math book, and it makes no effort to make it accessible to engineering background students. So one has to be careful about this book. Once you are comfortable enough with mathematical theories of integration, differentiation, then you can try to read this book. But in general, this Shift book I like because it is a balance between engineering background, so the perspective taken by engineering students and the perspective taken from a mathematical point of view. So it's a good balance. Okay, exact definition of Dirac delta function and what is U0. So exact definition of Dirac delta function is taken. So it is not really a function. So that's the main problem here, because in terms of function, a function must take a finite value at every point. But the Dirac delta function does not take a finite value at the point that it is defined. So at the Dirac delta function at z at let's say equal to some positive number a, uh, intuitively it takes infinite value at that point. It is not well defined as a function, but in terms of mathematical theory, it can be given conceptual background, and this is what's called a theory of a generalized function, or a theory of distribution. So as far as integration and Laplace transforms is concerned, you can always use the integral formula for the Dirac delta function, which states that the integral uh, f ft. So let me write down. So this is not a definition, but rather a property of the Dirac delta function. So let's say delta a. So delta function Dirac delta at t equal to a, and this says that if you have a function ft And if you apply delta A t dt, then this should give you the value of f at a. So this is the defining property of the derived delta function, which makes it so useful. And so I'm not going to give you a precise definition because it will be more, let's say, theoretical in nature. But so this is what's called a generalized function. So in the course, I gave some intuitive description of the derived delta function, a limit of some square function. So this was something like this. So one was this, the other one was this, and the other one was this. So it grows at t equal to a, it grows to infinity, and it shrinks in width but grows in height. So this is an intuitive description of the Dirac delta function, but it is not a precise definition. For a precise definition, you would have to learn about what are called distribution. So I will leave it at that because at this moment, just to compute the Laplace transform, this intuitive description is enough because we are only dealing with integral. U0 is the Heaviside step function at the point t equal to 0. So it takes 0 value for t less than 0, and it takes the value 1 for t greater than or equal to 0. This is the Heaviside step function for the point t equal to 0. Which is the best advanced route for transform? So this is something I already talked about. Sufficient conditions for existence of Laplace transforms. This is something that I already spoke about. We saw many, actually, not just one, but many sufficient conditions for the existence of Laplace transforms. One was for piecewise continuous functions. If you have a piecewise continuous function of exponential order, then it has a Laplace transform. But it could happen that the piecewise continuous function, so the function may not be piecewise continuous, let's say at t equal to 0 or at some other point, but the Laplace transform may still exist. So in terms of, for example, the log function, it is not piecewise continuous at t equal to 0. The Laplace transform still exists because it satisfies some other sufficient. So you can go back to the first week's lectures to look at the E sine t. Okay, so this is a computational thing. So if you are if you can try it yourself, I would be really glad to see your attempt in the discussion forum. This is not the right forum because it will take a long time to derive the formula. But you can look at, so you can write to me on the discussion forum and giving your attempt at solving this problem. I would like to see that you have tried at least to solve this problem. And then I will, if you're still unable to answer this question, then I will be happy to answer it on the discussion forum, but not here because it will take me a long time to solve here. Similarly, value of a unit impulse at endpoints. Unit impulse at endpoints. So this is a difference of Heaviside step functions, and I have given examples of such functions during the last week lectures, where we determined some. I think it was for, I don't remember precisely now, but I think it was for the simple harmonic oscillator. So a spring attached to a mass, and there was a function of constant value applied for, let's say, 1 second or 2 seconds, and then it stops. So you can model these kinds of functions using the difference of Heaviside step functions. and then you can solve it just fine. You know the Laplace transform of each L-side step function, and so you know the difference, the Laplace transform and the difference of two L-side step functions, and you can solve it easily. What is u0 if it is undefined? So you can take u0 to be 1. You can also put it any other value for u0, because as far as Laplace transforms, computation of Laplace transforms is concerned, the value at one single point will not affect the result of the integral. So you can put u0 to be 1, or you can put u0 to be 0, or you can put u0 to be any finite number. It doesn't really matter, because it is still going to be piecewise continuous, because for a piecewise continuity, you only need that the one-sided limits exist, and they may be different from the value of the function at that point. But even if the values are different from the left or from the right, and then it is still considered piecewise continuous, and you can still perform the integral, and you will find the same answer whether you take whether you change the value of the function at one point. It will affect the result for the Laplace transform. So you can take u0 to be 1. This is the convention, but you can also take u0 to be any other point of the y-axis. It will not affect, as far as Laplace transform is concerned, it is not going to affect you. Lerch's theorem. So Lerch's theorem is about the uniqueness of the inverse Laplace transform. So this is where what I said about changing the value of a function at one point. So as long as the difference of two functions is a null function, meaning that the Laplace transform of that null function is going to be 0, then the Laplace transform of these two functions will agree. And so the uniqueness of the inverse Laplace transform is only up to addition of a null function, meaning that if you have a function f1 and you can define another function f2 by adding a null function to f1. So f2 is f1 plus some null function nt. And then you can try to compute the Laplace transforms, and the Laplace transforms will be the same. So as far as the inverse Laplace transforms is concerned, uh, it is only determined up to addition of a null. Um, if on the other hand, if your functions are continuous, then the Laplace transform is going to be unique, because when you are changing the value of a function at a point, you are changing the continuity properties. It's going to be discontinuous. So once you have continuity, then Lerch's theorem guarantees that two continuous functions of exponential order, if their Laplace transform is the same, then the inverse Laplace transform gives you the same function. So then the inverse Laplace transform is unique. So that is Lerch's theorem. So I think I covered it in one of the lectures. So you can also go back and look at. I think it was in the third week of lectures. Okay, another question, and this is probably the last question I'll take because we're already almost out of time. About necessary and sufficient conditions. So this is something that we use in mathematics a lot, and these are terms that imply logical inferences. So um, let me see. So if you're talking about Laplace transform, so a sufficient condition for the existence of a Laplace transform means that if that condition is satisfied, then the Laplace transform exists. Okay, so this is a sufficient condition. Sufficient meaning that uh, once this condition is met, it is sufficient for the existence of the Laplace transform. On the other hand, there can exist Laplace transforms which do not satisfy those conditions, and this means that the sufficient condition you give is not necessary. Meaning that, for example, we have seen that there exist Laplace transforms of functions which are not of exponential order, and piecewise continuous. So, for example, the log function, and there are so it does not satisfy the sufficient condition of piecewise continuity on the whole interval 0 to infinity and of exponential order, but it satisfies some other sufficient condition. Okay, so there may be several sufficient conditions for the existence of Laplace transform, but none of them are necessary. So we cannot say that if if you know that the Laplace transform of a function exists, then it must have this property. So this is a necessary condition. Which, if you know the existence that the Laplace transform of a function exists, then you cannot deduce from that information that the function must be of this and this type. So that would be a necessary condition because it is necessary for the existence of Laplace transform. So this is the main difference between sufficient and necessary condition. A sufficient condition will only guarantee once that condition is met, and a necessary condition will guarantee some property of the function if you know that its Laplace transform exists. So this is the main difference between necessary and sufficient condition. This is a very basic terminology that we use in mathematics, and it is about the logical inference. When can you deduce one statement from another, and vice versa? So you can just look at in any mathematical book or even on Wikipedia, you can understand it. If you still don't understand, you can ask me on the discussion forum, and I'll be happy to answer um, uh, on the discussion forum. Another question is the Laplace transform of derivative that f is discontinuous. So I think on the discussion forum, I discussed this kinds of questions. So these are the derivative theorem for piecewise continuous function, and this derivative theorem, the usual derivative theorem fails for piecewise continuous functions, and there are some extra terms that one has to take care of at the point of discontinuity. And if you just look at the discussion forum, you can search for it, and you will find a very detailed post that I wrote explaining how to derive the derivative theorem for piecewise continuous function, and what is the formula for such a Laplace derivative in that case. I even gave for higher derivatives some examples where you can compute the Laplace transform higher derivative even when the lower derivatives are not continuous. So the usual higher derivative theorem requires you to um, have the all the so if you are concerned about the Laplace transform of the nth derivative, then you must assume that the function itself and all its derivatives up to order n minus 1 are continuous. So that is the usual high derivative theorem, but you can also have high derivative theorems when all the derivatives up to order n minus 1 are not continuous. And in that case also you can have a formula for the Laplace transform of the derivative. and you can refer to my post. And I also included some on my lecture notes, some formulas for this case. So you can also look at my lecture notes. I think it was in the second week of lecture notes that you will. Okay, so we are quite out of time for this live session. If you still have questions, please do not hesitate to ask on the discussion forum. I'm always available there until the exams, and I'll be happy to answer your questions there. So some of the questions like the Laplace transform of gt sine t, I think gt is the Bessel function, if you want to. So I can try to uh, answer there. Just post an email and I'll try to answer there because time is too short to answer such lengthy computations here. And continue to ask questions and continue to learn. And be very careful when you are trying to apply Laplace transform techniques. Especially, you have to check all the assumptions for a particular formula hold, so that you can apply the assumptions, apply the formula correctly to solving the problems. And then you will see that it's not that difficult to apply them correctly. And you will also start to see that there are some mistakes in the literature, in the usual well-known books also. There are some mistakes concerning these formulas. So be very suspicious. Always scrutinize what is being taught, whether it is in a book or whether it is in a lecture. And you should always ask questions why at each step, so that you learn it in depth, and you know where things can go wrong. Sometimes it is very important to know not only where things can go correct, in so not only important to know what works, but also important to know what does not work. So keep learning what does not work. Sometimes it is even more important to know. Okay, so I thank you all for asking good questions, and I hope you have enjoyed this course. Thank you um, from myself and from the whole NPTEL team. Even the conditions this time were quite difficult, I know, but still you stuck to it and you learned this course. So thank you all. Like I said, if you still have questions, then you can continue to discussion forum until the exam. Thank you.